I'm just going to go over the integrated rate law question where we're looking at the decomposition of compound X into Y and Z. And we've got the following data that we collect as a function of time, the concentration of X, and they ask us what's the order of this reaction. Well, the best way to answer this question is basically go ahead and make those graphs to determine is this a zero, first, or second order process. And to remember, if it's a zero order process, if we graph concentration versus time, that should be a straight line. For a first order process, if we graph the natural log of concentration versus time, that should be a straight line. And if it's a second order reaction, we would graph 1 over the concentration versus time, and that should yield a straight line. So let's go and make those plots. And we should see that here's our first plot for a zero order reaction. If we just plot concentration as a function of time, right, we don't get a straight line. It's not a zero order reaction. If we go and then make the plot for a first order process, natural log of concentration versus time, again, we don't get a straight line. It's not a first order reaction. And then the last one that we can try would be a second order reaction where we would plot the 1 over the concentration versus time. We can make that plot, and there you see we do have a straight line. Because this data represents a straight line and 1 over concentration versus time, we know our reaction is a second order process. So this is important because this helps us determine what integrated rate law we can use to help calculate the concentration of this reaction at a time later in the course of the reaction. And that's what we're required to do in part B of this problem, where we're given the rate constant for the decomposition of X. So that's rate constant is K at 1.6 inverse molars times inverse minutes. Calculate the concentration of X after 17 minutes. And so our rate law, because it's a second order reaction, would be K equals X squared. But more importantly, we need the integrated rate law, so that would be 1 over the concentration of AT equals our rate constant times time plus 1 over our initial concentration, A0. And next, we just need to plug in all the variables. So we've got 1 over AT, we've got our rate constant, 1.6 inverse molar times inverse minutes. And one thing that I checked and thought they were going to stump us on is maybe give us a rate constant with different units than our time frame, but fortunately they're both in minutes, so there's no unit conversions there. Our time is 17 minutes plus 1 over our initial concentration, which is 0.467 molar. And so fortunately we multiply, minutes will cancel out, and we multiply those two, and then we can add 1 over 0.467 to get A at time t equals 29.34 molar. From there, we'll just multiply across by A at time t. So multiply both sides by A at time t. That'll cancel out, and we'll get 1 equals 29.34 molar times A t, and then we just divide both sides by 29.34 molar. 29.34 molar, and we should be left with our concentration at time t equals 3.41 times 10 to the minus 2 molar. And so the hard thing to do is determine what's the order of the reaction. Once we determined it was second order by graphing, making the 3 different graphs, we knew automatically to use the integrated rate law for a second order reaction. And we could use that to determine, given what we had, the initial concentration, our time frame, and our rate constant, we could use this to determine what is the concentration at time t later in the reaction, in this case 17 minutes into the reaction.